All right, let's jump right into it. Welcome back to The Explainer, where we're breaking down the incredible engineering behind subsea production systems. Now, everything below the waterline that we've covered so far has been pretty still, structures just sitting quietly on the ocean floor. But today, we're tackling what is basically the spine of the entire subsea system, production risers. Welcome to the dynamic zone. So to really get the riser, you first have to understand the wild environment it lives in. I like to call this the dynamic zone paradox. Just picture it. Up at the surface, you've got a floating host facility, a vessel taking a constant beating from wind, waves, and ocean currents. It literally never stops moving. Meanwhile, thousands of feet straight down, you have a wellhead structure locked firmly into the seabed in absolute pitch-black stillness. And because of that exact paradox, chaotic motion up top versus dead stillness at the bottom, the riser takes a beating. It deals with relentless cyclic bending day in and day out. That mismatch makes the riser the single most fatigue-sensitive component in the entire subsea architecture. It is, without a doubt, the most stressed and vulnerable piece of hardware we're going to cover in this entire series.
So, what's its actual job? At its core, a production riser is a conduit. It's built specifically to route produced fluid from that stationary flow line or subsea tree on the seabed straight up through the water column to the topside processing equipment on a moving host. It exists simply because there is no other way to get fluid through the ocean while constantly absorbing that relentless motion for the entire operating life of the field.
Now, what's really interesting is how engineers actually quantify that motion. They use a heavy-sounding term, the Response Amplitude Operator, or RAO. But don't let the name intimidate you. The concept is actually super simple. RAO just measures how much a specific hull moves per unit of wave input. So a high RAO, the hull's heaving and swaying all over the place in a storm. Low RAO, it stays pretty stable. And this number is absolutely crucial because it dictates exactly what type of riser we need to select to survive that specific motion. Section 1, 2 Engineering Solutions, Conquering the Dynamic Zone.
How does subsea engineering actually solve this RAO challenge? Well, we generally rely on two primary solutions. Let's look at the first one, the steel catenary riser, or SCR. I absolutely love this analogy from the source material. Imagine an SCR like a garden hose draped in this graceful curve from a moving sprinkler down to the ground. It's a free-hanging pipe, no buoys, just sweeping and flexible. And because it's so simple, it is highly cost-effective. It absorbs the vessel's heave by just laying down a little more pipe on the seabed or lifting a little bit up.
On the flip side, we have the second solution, the top tensioned riser, or TTR. Forget the garden hose. Picture a fishing rod held rigidly vertical by a spring-loaded reel. The TTR is always kept taut, no matter how much the boat heaves or rolls. It relies on a mechanical tensioning system on the host platform, think massive hydropneumatic tensioners, to maintain a perfectly vertical profile under continuous tension. If we put these side by side, you can really see how they build into the overall field architecture. If you're using an SCR, you're pairing it with a wet tree host. Its superpower is flexibility, but its main vulnerability is touchdown zone fatigue. Now, if you're using a TTR, you're pairing it with a dry tree architecture. Its key requirement is maintaining that vertical tension, and its primary vulnerability is the mechanical limit of its tensioner stroke during massive storm heaves.
Section 2, the touchdown zone threat, where the riser meets the mud.
Let's zero in on that SCR vulnerability for a sec. I want you to visualize the exact point where that graceful curve of steel finally meets the mud of the seabed. It begs a really critical engineering question. After millions of wave cycles, where is a catenary riser actually going to break first? Think about how the energy from that floating vessel transfers down the pipe. It all comes down to what we call the jump rope effect. You know when you swing a jump rope, it doesn't snap in your hands, right? And it doesn't wear out in the middle of the air? The exact spot repeatedly slapping the ground absorbs way more cyclic stress than anywhere else. For an SCR, that spot is the touchdown zone. All that cyclic bending from the vessel's motion concentrates right there at the mudline.
So, touchdown zone fatigue isn't just a box you check during the design phase. It is the primary design driver in deep water SCR engineering. It's a lifelong, ongoing management concern. The damage is cumulative. The riser is literally accumulating micro-damage from every single wave over a 20 or 30-year field life. Because of that, it requires continuous fatigue monitoring systems and highly specialized inspection programs.
Section 3. The Illusion of Choice. A Downstream Consequence. Okay,
Here's the real aha moment for this explainer. We've talked a lot about these two riser types, but here's what most people miss. Riser selection isn't actually a riser decision at all. It's totally an illusion of choice. Let's walk through the logic chain here. Think back to our earlier explainer on field architecture. Step 1, the reservoir engineers say the well needs frequent wireline interventions. Step 2, to keep those intervention costs low, the operator selects a dry tree host with a motion-optimized hull, like a TLP or a spar. Step 3, because you now have a dry tree topside, a rigid vertical mechanically tensioned riser, the TTR, becomes absolutely mandatory. So the cause and effect is completely set in stone before the subsea riser engineer even sits down at their desk. If the macro architecture dictates a wet tree on a floating production system, the natural, cost-effective choice is obviously the SCR. But if the architecture requires a dry tree on a tension leg platform, you are mandated to use a TTR to maintain that rigid topside access.
Let's do a quick interactive check just to make sure we've locked this in. Imagine you're the lead engineer. Your company just selected a tension leg platform host featuring dry trees to allow for direct surface intervention. You need a riser. Do you order an SCR or a TTR?
You guessed it, the answer is a top-tensioned riser. The whole point of a dry tree architecture is having direct, rigid access to the well from the topside. A sweeping, catenary-shaped SCR just physically cannot provide the vertical, mechanically tensioned connection that a dry tree requires.
We've seen how the motion of the surface dictates the spine of our system straight through the dynamic water column. But that leaves us with a pretty fascinating question. Once that high-pressure, high-temperature fluid safely navigates the riser and is lying completely flat on the freezing seabed, what happens next? How do we push it miles across the ocean floor without it freezing solid? Well, that brings us to the incredible engineering of subsea pipelines and flow assurance, which is exactly what we're going to unpack in our next explainer. Keep learning, stay focused, and I'll catch you there.